Hi, everybody. My name is Alex Garibay. I am a software engineer at Dockyard. I've been with them for about almost a year and a half. And I'm here to talk to you today about scaling concurrency without getting burned. Some lessons learned while trying to push an application to the maximum performance by leveraging concurrency and some primitives within OTP. And my goal for today is for you to be able to walk away with some new concurrency patterns that you can apply in your own applications, and at the same time understand the subtle nuances of what comes along with pushing the limits and adding more concurrency. So my talk is based on a real-world problem we have worked on here at Dockyard. We had been working on an application called BlockScout, which is centralized around the blockchain ecosystem. So this application had two main goals. It's to catalog the entire blockchain, so Ethereum-based blockchains, historically and in real time as blocks are mined. And by that, I mean fetch all the data that's related to a block and all the transactions and all the ancillary data that comes along with it, as well as being able to provide a web interface to explore this same data in a meaningful manner. Many of you might be wondering, what is a blockchain? And this is how you might feel. That's all right. I'm going to give you a really short version. You can think of the blockchain as a distributed ledger that has been written inside of blocks. So you'll have a group of nodes that come together to form a consensus to say that there have been this list of transfer values between addresses, and we'll write this to a block and we'll commit it. So each block contains a list of transactions that are committed and they're read-only, and it forms an append-only style linked list. You can think of a block at a high level of containing a few fields. One would be a hash, which is a unique identifier, a previous hash, which would point to the previously mined block if this were the new block, and the list of transactions that are going to be committed to the ledger. And when you put it all together, they form a linked list where they all are chained together for millions and millions of blocks. The previous architecture of this application was in a little state of that needed a little bit of work and some fine-tuning. So when we came on to the project, what we saw immediately were some things that you might find in Rails applications, such as worker queues, where you create some tasks to go execute in Sidekick, but in the Elixir world. And the important data on the blockchain was fetched serially, one at a time, not really in any concurrent manner. And this is really how the performance of this application really felt when you ran it. So we set out a few architecture goals on this application when we came in. Firstly, we really want to be able to embrace OTP, embrace Elixir, and all the primitives that are given to us to build powerful concurrent applications. We also want to be able to catalog the entire blockchain as fast as possible and as hard as possible, and at the same time be able to efficiently broadcast events in the system to say that new data is available for the UI for a nice real-time user experience. And just to give you an example of how large the data set in the Ethereum chain world, Ethereum takes up around 1 terabyte of data on any of the connected nodes. And in Ethereum, there are over 6 million blocks currently. So it's a little unrealistic for people to have that whole terabyte of blockchain data on their systems just to explore in a sort of meaningful manner. One of the immediate things we saw when we started digging into this application and where the bottlenecks were, there was a single gen server that was responsible for making all outgoing requests to an external API that we relied on to fetch data from the blockchain nodes. And it takes several requests to fetch all the data related to a single block. So you can imagine an API for that Gen server where you make a call with the entity that you want to fetch. So for instance, we wanted to fetch something by block number. This goes out, makes the external request, comes back, and then you get your data elsewhere in the application, you store it. And you might be wondering why this is an issue. Due to the nature of how processes work and messages, the message mailbox for a process can only handle one message at a time, so things are handled serially. So that means that you're limited to one request at any given time due to the architecture of this process. And that makes it to where your I/O bound and your throughput is determined by how fast the external API can process your request. And within Elixir, there are plenty of primitives for us to build our applications on, and one of those is tasks. So if you're unfamiliar with tasks, they allow you to perform asynchronous work in separate processes. And you are able to spawn a new function with spawn a new process with a function that you want to execute in that process. And you can await for the results, or you can continually check for a result to come back. And one characteristic of tasks is that they are both linked and monitored by the spawning process. And I'll come back to why this is important in a few minutes. So we started to break out that external, or that Gen server into functions that we can leverage elsewhere and not rely on a single Gen server. So when we started to break it out, we used task async, fetch a block, get the data and await, and then store it. And this really allows us to build up the concurrency in a slow but like a building block of Legos. So what we can do is start creating several tasks that run at any given time and leveraging concurrency. And due to the nature of this external API, if you're unfamiliar with a JSON RPC, you pass in a list of procedures that you want to execute in a request. And the previous architecture only ever allowed for one operation to happen at any single time. So we're able to perform multiple operations per request and then fire off multiple tasks at the same time and truly improve our concurrency. And we can do that by leveraging task.async_stream. That allows you to pass a list of items and perform a function on every single one of those items in separate tasks. And again, we can leverage the task module and await for those with yield many. After that rewrite, we would take a list of block ranges, fire off task async_stream, fetch those blocks, then await for those results to come back. This was a great initial step to improving the performance in our application, but unfortunately, this incidentally caused problems. This cheap concurrency caused a lot of problems for the load-balanced Rust servers that we were hitting. We accidentally brought them down with our developer laptops with minimal work. But to be fair to Rust, Elixir had the easy part of just firing off cheap concurrency. And due to these errors coming back from these load-balanced nodes, we were getting 500s, timeouts, anything. And whenever you have a task fail, it's going to raise an exception in your hierarchy of supervision, and it might even end up causing your application to crash. And whenever you're dealing with I/O-bound work, you're going to need to do some fine-tuning to make sure you find a nice balance between performance and making sure you don't hammer the services you require. So within task async_stream, there's a an option that we can leverage to limit the amount of concurrent tasks that are executing at any given time. So what we had to add in for this was using the max concurrency flag and just limit that down to just a little bit smaller amount of tasks going at any given time. So by default, task async_stream uses the amount of logical processors that are assigned to the beam. But conversely, if you find that the external servers that you're trying to hit can still handle the load, you can up this number until you find that nice balanced medium. But when you're starting to increase this concurrency, there's a whole plethora of issues that you might not think about right away that can really cause problems within your application. So one thing you have to think about when you start using tasks is, how do I restart those tasks? How do I rebuild my working set of data? What happens when the external host I'm relying on goes down and I'm starting to get 500s? Or what happens when I'm starting to get rate limited by this external server? How do I respond to this and not bring down my application with other errors? As with all things that we say in Elixir, put it in a process. So what you can do is put it in a gen server. And this allows us to have finer control over the results coming back from our tasks. But it's really important to design your process to recover its state on its process restart. So it's key to design your processes with failure in mind. And then we can leverage supervision throughout our application. Before I go any further, I want to revisit what links and monitors are if you're unfamiliar. So when we say two processes are linked, it opens up a bidirectional communication layer whenever one process receives an error and it crashes, that's going to propagate to the linked process. So if we have process A and B and we say they're linked together and process B crashes, that error is going to propagate to the other process, so process A, and it's going to go down. And if you're unprepared to handle these sorts of errors, you're going to be woken up at night with a page. And monitors are similar. So it only goes one direction, though. So you can say that one process will watch another one, and if the other one that you're watching goes down, you'll get a notification. So say we have process A and B. And process B goes down, and A is watching B. A will still stand and get a notification, and you can handle a result that way. And it leaves us happy. So there are a few characteristics that you may be unaware of whenever you spawn tasks within a gen server. So one characteristic is that they are both linked and monitored. A message is actually sent to your gen server with a message that the result is ready. Due to the fact that they would be linked, if a task crashes, it will also bring down your gen server. And again, I want to hammer this in. It's important to build state with failure in mind. So how would we go about starting a task within a gen server? You might want to start your init block and build your state and start fetching the work or performing the work that you need to do. So you start your task, and then you run the function inside of task.async. And if you look closely, there is a ref property on your struct, and you're going to want to keep that in the state of your application, or sorry, excuse me, the state of your process. So you'll run your task and put the reference inside of your state. And in the event that your task is successful, you're going to receive a message inside of your process's mailbox. And we can use this to our advantage. You'll receive a two-element tuple, the first element being the reference, the monitor of the task, and the result of the function that you execute inside of your task. And we can pattern match the ref that we receive in the tuple to the ref that we have stored in our state. The first thing that you want to do is demonitor the reference, because you'll continue to receive messages inside of the process's mailbox related to the task actually completing. You can do something with the result like store it inside of the database, queue up more work, and then clear out your ref. And in the event that your task actually fails, it's going to crash, your process is going to restart, but we can continue working on. One of the lesser known things within the task module is supervisable tasks. You can dynamically spawn new tasks that run under a separate supervision tree. These tasks are only monitored and they're not linked. And I'll get to why that's important. And you'll still receive callback messages in your process's mailbox. And how would you go about using that? You're going to want to add a new task supervisor to your supervision tree and give it a name. And just like before, we're going to start a new task to perform expensive work. However, you're going to use task.supervisor async no link, and you're going to want to pass in the task supervisor you want to use and the function that you want to execute inside of the task. Then you save the ref that you get from the task to your state. In the event of a successful task, you're going to get the same exact format of the two-element tuple with the ref and the results of the task. You're going to want to match the ref to the ref you've saved in your state, demonitor the ref, continue on doing work, and so on and so on. However, in the event that your task fails, you are not going to crash your process. You're actually going to receive another message in your process's mailbox with a 5-element tuple with some things that you can leverage. But the important thing to note here is that you'll be able to handle failure in a more meaningful way and build up a stateful response to failures. So what you could do here is you could potentially log, or in the event that you're getting rate limited, you can start performing exponential backoff. So there are a few key differences between tasks and supervised tasks. For a task is linked, it is monitored, and it's awaitable by the calling process or the spawning process. And with supervised tasks, it is solely monitored by the spawner. And you might be thinking, when would it make more sense to use a supervised task versus a non-supervised task? The primary use case is whenever you want to build a stateful task lifecycle. And the example I give is exponential backoff. You could keep track of how many times you try to perform a task and add some sort of jitter and some time in between subsequent requests to give the external server that you're trying to hit some more time to catch up on work. And also, whenever linking isn't desired, so if you don't want a task that airs out to crash its owner, that would be a good time to use a supervised task. So even though we're pushing our data, our concurrency much higher, we're needing to save this data off in a meaningful and performant manner, or your database is actually going to become your new bottleneck. So we have to do this and maximize how we write to our database. Due to the fact that we're fetching data much more frequently, we're having much more throughput, we have to commit this data to our database in a performant manner. And if you were to rely on this using repo insert, you're going to have terrible performance, and then your database is going to become your bottleneck. And for the blockchain, when we're fetching all of our data, we actually need to commit several entities to our database for a single block. Well, what we can leverage is ecto repo insert all. And what this allows us to do is insert multiple records into our database with a single query instead of maybe hundreds, thousands of extra inserts. One caveat is that it bypasses schema validation, but it's incredibly fast. So for example, you can insert tens of thousands of records using repo insert all within just a few hundred milliseconds. When we rewrote this sort of data insertion, we would get a list of blocks, so a list of block parameters. And to use repo insert all, you need to specify the target struct that you want to use, or even a table name, the list of parameters that you want to insert, and any options you need to pass to insert all. But there are a few caveats to this. You're unable to use change sets directly inside the list of data that you want to pass to insert, but that doesn't mean that you can't use change sets. What you have to do is apply your change set validation much higher up in the execution, and then extract out those params to a plain map when you're doing the insertion. And you cannot rely on auto-generated values, such as timestamps, to be generated for you when you use repo insert all. So even though we were able to do this and remove the database as a bottleneck in terms of insertions, we ended up still getting burned. So when we're having multiple processes trying to write the same data at the same time, there's a high chance that you're going to run into sort of any sort of data conflicts. And one thing that you might have to do is resolve those conflicts in a meaningful manner. So within our database, we only ever want to have unique blocks committed to our database. So we wanted to target the field number in our database as the conflict target. So if we ever encounter two blocks trying to write, if we're trying to insert another block with a number we've already detected within our database, we can specify how we want to handle that. What we wanted to do was just replace whatever was there, so we specified the onConflict option with replace all. And the reason we have to do this is because we can't do a query on our database to see if the data is there prior. We might have another process come in and do an insertion between the time when we are querying the data and the time that the other process tries to insert. And additionally, there are times when you might be having deadlocks, which is a little bit more rare. Luke Imhoff has an article of how he resolved this within our architecture, and I encourage you to check it out. So now that we're having a lot more data in our database, we still have to worry about the problem of fetching that data efficiently and not overloading our database server. So in our database, we actually end up having tens of millions of rows. And within these tables, there are fields that signify whether or not we need to perform extra data asynchronously. And if we were to use repo.all in a query for this table, we're going to have to wait for all this data to be accumulated on your database engine. So all that data is going to be accumulated on the Postgres side before coming over to the Elixir side. And this query is going to be a blocking operation. So it's important to note that this can be a huge issue because you're doubling up on memory on between your database server and your application for a short period of time, and you may end up having memory issues. I was trying to run this the other day, and I actually started causing pages trying to test this out. Luckily, Ecto has some really great things built into it, like RepoStream. This allows us to create a lazy enumerable for our query, and it is much more memory efficient because values that are calculated by the database engine are sent over directly to our application without having the need to accumulate on the database engine side. Like I mentioned, one of our tables is marked with asynchronous work, with some fields for asynchronous work. We build up a list of our data just by appending to a cons list, and we start with an initial list of empty items. So we run RepoStream on our query, and we build our working set. But it's important to know that once you start reaching a data set size of several million rows, this query still may end up taking a long time. When we started doing this in production, we actually ran into issues because these queries were timing out because it took too long to execute. So what the solution here is to use the option of timeout infinity. You have to pass that to both RepoStream and RepoTransaction. So it's important to note that once you start reaching a significant data set size, you may have to start playing with the timeouts to make sure you don't crash your applications inadvertently. Another aspect of our application relied on a read-heavy cache. It was responsible for going out and fetching external market rates between other cryptocurrencies and the US dollar amount for those cryptocurrencies. So a common pattern you might see within other applications, other applications is to use a gen server or to use an agent, and you store your data set inside of the state of that process. But once you reach a certain data set size and you have multiple processes all trying to read from that same process, that cache is going to end up being your bottleneck. And within Elixir, we can leverage ETS with a reconcurrency flag enabled. And if you're unfamiliar with ETS, it stands for Erlang Term Storage, which is built into OTP. And it's incredibly fast. And whenever you create an ETS table, the the table that creates, excuse me, the process that creates that table is the only allowed reader by default. And we can actually configure this to be optimized for reading directly from this table. And what that looks like is when you start your process, you create a new table. The important thing here to note is that there is a public option enabled as well as a reconcurrency flag. So after that quick rewrite, if you notice the bottom two functions, all tickers and fetch tickers, we can actually directly leverage ets and fetch directly from ets without having to rely on message serialization to our process. So the benefit of this is it allows any process to read directly from ets, and we're no longer relying on the message serialization to our process. And a really cool feature of ets is that it could actually be used as a rate limiter. Chris McCord has an article where he demonstrates this, and I encourage you to check that out. Another aspect of this application that we wanted to achieve is efficient data dispatching. So we wanted to be able to broadcast events within our application whenever new data is inserted or specific events happen. And we wanted to have an easy subscription mechanism and an easy publication mechanism. And what we can leverage within Elixir is registry. Registry is a local node process registry, so it's not distributed across nodes. It's only local to the node you're working with. But processes can register under specific topics, and they can automatically be removed whenever that process crashes. And also, it was born from Phoenix PubSub, which is awesome. And to leverage this within your application, you just need to add a new registry and give it a name. One key thing to notice here is that you want to set the keys to duplicate. And to subscribe to a topic, you want to call register with the registry you want to target and the key that you're interested in. And to publish to a topic, you use dispatch with the registry you want to target under a specific key. You'll receive a list of entries where you have a two-element tuple of a process PID and a registered value that you use when you subscribe, which it doesn't necessarily matter for our use case. So whenever we start inserting all of our blocks, we can send a notification to interested parties like a UI or a client that's connected to let you know that there is new data available. You should probably refresh. So I want to summarize or come to a close and let you know that Elixir is great. Yeah. Thank you. I didn't expect applause there. Elixir is really fast. It's really scalable. We all know that. But Elixir itself really provides a lot of the tools that we need to build highly concurrent applications fairly easily. But even though it gives us all these tools and allows us to create cheap concurrency, it's really important to know where these tools accelerate, where they fall short, and the sort of subtle nuances that come along with using these powerful tools. So thank you for listening. Again, my name is Alex Garibay. You can find me on the internet. And one final note, if you haven't entered for some free Chris's time, make sure you enter because the drawings will end right after my talk. I'm not going to be able to take any questions, but you can find me right outside in the hallway right after this. Thank you.